roots of complex numbers. This is what we're looking at next, and I believe this is the last part of chapter 6 that we're going to look at. Now we know that conceptually, and we talked about this yesterday, x to the 6 minus 1, well, we can factor that into x cubed minus 1 times x cubed plus 1. Now since these are both cubic, we can factor those again and get x minus 1 times x squared plus 1 times x minus 1 times x squared, or sorry, x plus 1 times x squared minus x plus 1. We can factor it this way. And the x minus 1 and x plus 1 will solve out to be x plus and minus 1. And then the other two quadratics will simplify to this here. So we can factor this one using the theorems and methods that we have already. Now the complex number, for a complex number u equals a plus bi, is the nth root of the complex number z when z is equal to u to the n, which is equal to a plus bi to the n. And this, by definition, is the nth root of a complex number. Now, to find a formula for the nth root of a complex number, let u be the nth root of z, where u is equal to s cosine beta plus I sine of beta, and z is equal to r cosine of theta plus I sine of theta. And this here, we're just working through to get to the formula. By De Moivre's theorem and the fact that u to the n is equal to z, you have that s to the n cosine of nb plus I sine of nb, that to the nth term, is equal to r cosine theta plus I sine theta. Now taking the absolute value of each side, it follows here. We get this here, cosine of n beta plus I sine of n beta is equal to cosine theta plus I sine of theta. And really we're saying that the cosines are the same and the sines are the same, because that's the only way that these can be equal. Because both sine and cosine have a period of 2 pi, these last two equations have the solution if and only if the angles differ by a multiple of 2 pi. Therefore, this must exist. But really what is key is this formula here, finding the nth root of a complex number. And this here will find any root of any complex number. So z of k, z sub k is equal to the nth root of r times cosine of theta k over n plus I sine 2 pi k over n, where k, comma 1, comma 2, comma n minus 1. N is the root, or n is the root, has indistinct nth roots given by this here. Indistinct roots. So if we're looking at a cubic, well, how many roots should we have? 3, yes? Now, if you notice, the value of k starts at what? 0. Well, we have 3 distinct roots, yeah? So n would be, cube, it would be 3, right? Oh, it's going all the way up to n minus 1. You're good. All the way up to n minus 1. So 3 minus 1 is 2, yes? So for values of k, I would have 0, 1, and 2. Well, 0, 1, 2 is how many? We still have 3, yes? And that's where we get n from. We have 3 roots. 4, 5, 6, it's the same. And that gives us some of these values here. Now, where k is greater than n minus 1, the roots begin to repeat. That's why we stop. Because if we go higher than that, the roots are just going to be the same. They're going around a circle. But we're talking about the complex plane. Well, that's the main thing we talked about in a complex plane, a circle. So if we go past n minus k, and when k is greater than n minus 1, we're going past 360, or we're getting, not past 360, let me take that back. We are going to repeat the values. We're going to get the same values repeated. Now for sum, if n is equal to 2, it's not going to take that long because we only have 2 roots. So really we're talking about n minus 1. Well, 2 minus 1 is 1. So if we have a k value greater than 1, it's going to repeat. That's not going to take that long. Okay, let's write it again. How about n equals 20? It's going to take a while for this to repeat because we're going to have 20 different roots we'll have to take, and it wouldn't be till the 21st root that it would repeat. So some, it takes longer. We're not going to have a 21st. We're not going to have 20 roots. I'm not going to do that to you. For instance, k equals n is the angle theta plus 2 pi n over n. Well, we can split that up. Theta over n plus 2 pi. Because 2 pi, the n and n would simplify out, leaving us with just 2 pi. So we would just have whatever the starting angle was over n, and it's just going to add 2 pi to it. It'll repeat. Because it's almost the same as saying k equals 0, because those are the first ones that it would repeat. And if k is 0, well, inside here, it's really talking about theta plus 2 pi k over 2 pi, because that's what we started out, or not 2 pi, over n. Because we're talking about this here. Now, k is what? 0. So this whole part's gone, and we just have theta over n. Well, wait a minute. If I add 2 pi to it, it's going 1 full rotation, and I'm back where I'm at. So theta over n and theta over n plus 2 pi are the exact same value. That's why they're saying once n, k becomes greater than n or equal to it, we start repeating. We start repeating these values. Does that kind of make sense? Yes? Okay. The formula for the nth root of a complex number z has the nice geometrical intercepts as shown. And they're using a very mathematical version of the word nice. Because nice, I think, for y'all is not this picture here. Because these are not, in the average person's version of nice would be a whole number. These are not nice whole number terms. It is a nice mathematical picture. It's a nice representation of it from a mathematical point of view. For them, this version of nice that they're using for this here would be something that a mathematician would consider nice and would solve on a whim. Probably for the average person, it'd be like, oh, I'm going to go out and get ice cream. This is not the average person's version of nice, I wouldn't think. But I digress. Note that because the nth root of z, nth roots of z all have the same magnitude, nth root of z, nth root of r, they all lie on a circle of radius, the nth root of r, with the center of the origin. That's why we get that nice picture. Furthermore, because successive nth roots have augmentations that differ by 2 pi over n, the nth roots are equally spaced around the circle. You have already found the 6 roots of 1 by factoring and using the quadratic formula in cubics. Example 9 shows how you can solve the same problem with the formula for the nth roots. So we're going to look at this here, and I mean, there's an example in your book kind of showing you this. So you don't have to look at that there. What we're going to look at is this here. Now, the formula because I have it written up here on the board. You have it in your book. You can kind of reference back to it, or if you need to, I mean, skip back the video to where the formula shows back up and write it down if you didn't get it. But we have this here. Now, the formula is in terms of r and theta. Well, might as well write it down. Because we have the nth root of r cosine of theta plus 2 pi k over n plus I sine of theta plus 2 pi k over n. Now, if you notice, there's a few things that we're missing. One of them is n. Well, not that we're missing it, we just haven't stated what it is. Well, what would n be? How many roots are we taking? Find the 3 cubed root, because we're talking about cubes, we're talking about 3. So the 3 roots, so n is 3. Well, k is going to start out at 0, 1, where do we stop? 2, because we go to n minus 1. Well, 3 minus 1 is 2, so we have those. Now all we're missing is what? And theta, because once we get r and theta, we have all the missing pieces. Now, r is equal to the square root of 2 squared plus 2 squared. Which is 2 square root of 2. I'm going to leave it as a square root of 8. And there's going to be a reason why here in a minute. I'm not going to delve too deeply into it, but it'll make more sense once we actually start putting things together. Theta. Tangent inverse of b over a. So it would be 2 over. Now, right, it would be negative 1. Now, since, what quadrant are we in? 1, 2, 3, or 4? Are we in the first or second quadrant? Well, I mean, first or fourth, sorry, yes. You're giving me that question, look, yes, it's first or fourth. Because first, is it going to be in the first or fourth? This convoluted placement of the where this is located. Because what we're trying to get at is that tangent inverse will only give me degree measures in the first or fourth. It's going to be in one of those two. Because here, it's going to give me a negative angle. Here, it's going to give me a positive. Now, if we look at this here, negative 2 and 2. The negative 2 gives me the x. The 2i gives me the y. So since the x value is negative, we're in second or third. Since the y value is positive, it's in the second, because that's where it's going to be located. It's going to be located up here. Questions on this here. So what that means for us here is once we take tangent of, well, negative 1, we get what? Negative 45 degrees. Well, we can't take degrees. You know why? Well, both of our things have it in terms of 2 pi. Well, actually, we can look at our unit chart. 45 degrees is the same as pi over 4. So this is negative pi over 4. So that gives us this angle down here, yes? Well, if I want this one here, I need to add pi. Well, what do I have? I really have negative 1/4 plus what? What's 1/4 minus 1? 3/4. And we can add pi on top, and we have this here, yes? Now, if you were thinking maybe, well, couldn't we have just made pi over 4? Do we need to make it positive and then find it? Well, we would, but we wouldn't add pi anymore, we would subtract it. we would subtract pi over 4 from pi. Because if I made it positive, the positive angle going the other direction, it would give me this angle. And get back to the correct angle, I need to go the other direction. I need to subtract it, not add it. It works out that either one of 1 or 4, if I add pi to an angle in 1, it'll get me to the correct spot. If it's in quadrant 4 and I add pi, it'll get me to the correct spot. So we don't have to worry about this here making tangent inverse positive, but giving us a positive angle by adding 2 pi, because then we'll just have to subtract a pi from it. Because if I add 2 pi to get this angle going this direction, well, I went too far. I've got to backtrack. So adding, that's a long way to say, whatever tangent we get, if it's not supposed to be in the first or fourth quadrant, we have to add pi to it. If it's in the fourth quadrant, if it's supposed to be in the fourth quadrant, then we have to make it positive. So the fourth quadrant's the only one we have to add 2 pi to get the correct positive angle. The rest we can just add pi or leave it be. Which quadrant would we leave it be? 1. If it's in quadrant 1, it's where it's supposed to be. 2 and 3, we have to add pi to whatever the angle is. And if it's in quadrant 4, we add 2 pi, so we get it back to being positive. 3 pi over 4. Okay. Now we need to get down to the nitty-gritty, and we're not talking about the Flyers. It's a joke to myself. The mascot for the Flyers, the Pittsburgh Flyers, or the Flyers for the NHL is Gritty.
Oh, is it the one that's like...
So let's look at this here. So let's fill in. So we'll start off with the first one. Now, our n is 3. So we're starting off, so we'll call this z 0, because that's our first root, because this here is equal to z a. So we have the third root. So what is r? So we have the third root of the square root of 8. This is why I did not simplify it to 2 square root of 2, because we would have been taking the cubed root of the 2 square root of 2. That would have been a mess. We'll simplify this here in a second, but I want to fill everything else in first. Now we're going to have cosine of, well, our angle is 3 pi over 4 plus 2 pi. Now what is k? 0 over 3, because that's our n value. Plus I sine. We'll have the exact same thing. 3 pi over 4 plus 2 pi times 0 all over 3. So we have this here. Now, this here I would do off to the side. I'm going to do it underneath so that y'all can, if you need to go back and rewatch it, you can see it here. Well, 8. Now, the nice thing we know about radicals is we can change them to fractions, exponential fractions, because the number inside goes on top, powers inside the radical go on top, roots go on bottom. So this would be 1/2. And the cubed root would be powers of powers multiply. So 1/2 times 1/3 would be 1. Now, 8 is the same as 2 to the what? Third. Well, again, powers of powers. So I have 2 to the 3/6. Well, 3/6 is what?
Square root of 2. Yeah.
So that's why I said I would do this on the side, because otherwise if we did this in the problem, I would have had to rewrite this out 1, 2, 3, 4, 5 more times. No, this is scratch work. So square root of 2. So we did that on the side. Really, so I can come back in here and say, this is the square root of 2. This value does not change across all the roots, because once we find it, the nth root of r, we're going to keep it the same all the way across. I'm not going to rewrite the cubed root of the square root of 8 anymore in this problem, because the cubed root of the square root of 8 is the square root of 2. So we know that already. Z naught, square root of 2. Now, looking back at this here, cosine of 3 pi over 4 plus 2 pi times 0 divided by 3. Well, 2 pi times 0 is what? 0. This whole thing is 0. That whole thing is 0. So what I'm left with is 3 pi over 4, well, cosine, yes. Cosine of 3 pi over 4 divided by plus I sine of 3 pi over 4 divided by 3. Well, we do need to simplify this here. Yes, because what we get is pi over 4. Now again, this is, I'm going to show you this here because this really is scratch work. Because 3 pi over 4 divided by 3, well, it's really over 1, yes? Well, we don't divide fractions. I changed to multiplication and pi over 4. So it worked out. That's how it's simplified. And exactly, if we do cosine of pi over 4, we got square root 2 over 2. And sine is going to be square root 2 over 2. So how do we know that? Well, that's the only one. 45 degrees is the only time sine and cosine are the exact same, or any multiples of it. They have the same. The signs change around the circle, but it's pretty much square root 2 over 2. The signs just alter. Well, guess what we have to do now? Well, what's the square root of 2 times square root of 2? 2. 1 plus 1i. Questions on this here? How do you feel about this so far? Awesome. How many roots do we have? Guess what we do next? We find the second one. How many times are we going to do this? We're going to do a total of 3. We're going to do this 2 more times.
Yay.
That's why I said I will not give you a root of 20, because we would have to do this process 20 times. It's not that this is, it's just time consuming. Okay. I'm going to erase this here. Okay, so we found Z naught. Done. Z sub 1 is equal to, well, the square root of 2. Because again, our first one would have been the nth root of r, so the cubed root of the square root of 8. We already know it's the square root of 2. We're not going to rewrite that. Inside, we're going to have cosine of, well, it was 3 pi over 4, plus 2 pi times, well, k is what now? 1 over n plus I sine of 3 pi over 4 plus 2 pi times 1 over 3. And this n should be a 3. Now, you might be very tempted to say, well, this is going to just repeat because of the 2 pi. No, we're dividing 2 pi by 3. At this point here, to save on time, 3/4 plus 2 divided by 3 I went on and just plugged in 3/4 plus 2 divided by 3, the whole thing in there. It gave us 11 pi over 2. Now, if we take cosine of that, minus square root 2 over we get this here times the square root of 2, 3 minus 1 over 2 plus I times the square root of 3 minus 1 over 2. Yep. Now, if we do the next one, z of 2, we'll still have the square root of 2. Now, we're going to do this again tomorrow because I am 19. That's a 19. 19 over 12 pi, because we're plugging in 2 times 2 pi. So that'd be 4 pi. So 3 pi over 4 plus 4 pi over 3 would give us 19 pi over 12. Cosine of 19 over 12, 19 pi over 12, would give us the square root of 2 times the square root of 6 minus the square root of 2 over 4 plus I sine negative square root of 6 minus the square root of 2 over 4, which, kind of like the last one, we'll get square root of 3 minus 1 over 2 plus I times negative square root of 3 minus 1 over 2. And if you notice, Z1 and Z2 are the same. They're close to the same. They have some different signs. And that's normally how this is going to work out. A lot of them will have some that match up, especially with the imaginary terms. They'll have pairs.